So good morning, everyone. I thought yesterday was just fantastic. I felt like a time traveler, being propelled back and forth over these 50 years. And I'm afraid I have nothing comparable to offer because I've not been around that long. But I have been doing some thinking about when did my first encounter with structural chemistry take place. And it happened to be as a stamp collector. So round about the age of 11, this particular stamp entered my collection. And no, it wasn't the start of my career as a modeler. I looked at it, didn't understand it, and went on to other things. And about 15 years later or so, I recognized that looking at structures is actually more fun than looking at stamps. But it's also a nice introduction to what I'm going to say in the first part of my talk this morning. Of course, the stamp commemorates Barton's Nobel Prize in 1969 on conformations analysis. And it shows a structure that you should all be familiar with. And the question I'm asking is, has textbook knowledge on conformations actually progressed since then? What do people know about conformations? And I think we as a community, whether we're in material science or in drug discovery, we have an ongoing obligation to further that knowledge and to really be that educational community. And I'm just going to share in the first part really just a few thoughts about how that could be done and how we at Roche think about these kinds of things. And this will be followed by Klaus Müller, who's really been the pioneer at Roche in structure-based design and looking at structures, who actually taught me a lot about what I know today about conformations and interactions. So off we go. So one thing I think that could really be helpful if we did more of this would be to use analogies when we go through looking at structures and conformations. I'll start with a simple example here. So you've all heard about Allylic strain. You know that this is the type of interaction where this 1,5 repulsion here is avoided, and there's a strong avoidance that you see in the gap in this histogram. You all know about this, and then you could say, well, that's all good and fine, but Allylic systems of that type don't really play a role in drug discovery, and then you can forget it again. But really, there are many systems that you compare with this and say, well, really, amides, either way of looking at them from the carbonyl perspective or from the substituent perspective here, actually are allylic systems that avoid the exact same type of arrangement here. And all of a sudden, that kind of knowledge makes sense, and it can be compared and put into perspective. And then you can start to see that really tertiary amides have a certain reason why they're going out of plane, the substituents are going out of plane, orthogonal, why anilines of this type are also, in a way, allylic systems, and also things like these effects that acylated piperidines and derivatives have axial orthosubstituents, which is something that still is fairly unknown and unusual for many people when they look at structures like this for the first time. So the help of these analogies is really useful. Another thing is, it does make sense to think in series and to think about conformations as sometimes as a continuum of effects over a certain series of compounds. It's just one picture out of the conformation review from 2008 that we wrote, where if you look at essentially the same shape of system that has a saturated 6-membered ring in the center and then something like a phenyl group here, and you progress from phenyl cyclohexene to these aniline-type systems, piperazines, to systems that are more planar, more conjugated, where in the end the difference between axial and equatorial actually disappears, and you can start to really appreciate more what kind of space you can cover with these kinds of structures. And there's one nice example in the CSD where actually both the pseudo-axial and the pseudo-equatorial conformation appear in one crystal structure. So the energy difference between those two seems to be very, very small. So this is the second point. The third point is that it is helpful to increase the number of templates that you have in your mind a little bit. So usually, of course, we think about alkyl chains and gauche effects, and then maybe cyclohexane and cyclopentane, but when it comes to seven-membered rings, then many of us are lost already. And then there are drastic effects because, of course, depending on the nature of the seven-membered ring system, the shape of such structures are dramatically different. And depending on how these double bond equivalents are distributed over the ring system, you can get very, very different effects. Again, these are just simple examples, but this is just speaks to increasing the repertoire of things we have in our minds a little bit. And when Colin visited us in, when was it, March this year, maybe, in Basel, he brought a little presentation that contained, I think this is something that he has on an ongoing basis, interesting cases where structures play a role in drug design. And he brought one example that I'm picking up here and just using as an illustrative example of how you can use the CST to gain a little bit of knowledge, even for cases where there's relatively little data out there. So this is a compound you may all know, suvorexant. It's an orexin agonist that came out from Merck. And it has some of the features that I've talked about. So it has this axial methyl group, axial in quotes here because it's just orthogonal. We don't know that it's axial yet. Then it has an interesting seven-membered ring system with two planar nitrogens. And of course, there's the question of what's the overall shape and structure here. And there was a hypothesis early on in these projects, especially at Merck, that this compound would take on a U-shaped bioactive conformation. But if you now get the structure and you want to know a little bit more about what are likely conformations of this compound, then you could look at it in the following way. You could say, well, I'm interested in this piece really, and what I have is a structure that has two sp2 centers distributed in this way, and so the potential templates you could look at in the CSD are a little bit broader maybe than just that exact substructure, of which you find only one, I think, representative, at least when I looked in the CSD. So you can do the search and you can find around about 20 interesting structures, and they fall into two conformation groups. Of course, you have to look at the conformations in the right way, so you can actually compare them visually in a nice way. And one of those conformation groups is a kind of a twist chair where the two substituents point in different directions. And the other family is the exact same twist chair, but this time the two substituents point in the same direction. And here are two examples. The other thing that you can observe is if you look at the various structures of this type, that they actually have quite a variety in terms of how these different exit vectors relate to each other. So there seems to be quite a bit of flexibility in terms of how that exit vector sort of bends relative to this other one. There's a 50 to 90 degree range. This is interesting information for thinking about bioactive conformations, of course. Now, in this particular case, the solution is known because by now there's a crystal structure of this compound, which was solved recently, earlier this year. And there's a published crystal structure of the compound itself. And you can see that exactly the two types of conformations actually appear here. So in the small molecule structures, you have this conformation 1, which has the exit vectors in two different directions. In the active bioactive conformation, it's the other one. But if you look very closely, we actually looked at the way the ligand was resolved here. So this is it. This is the conformation. What they've put in there is more like a boat-shaped conformation. This is based on what you've now heard and seen from the CSD, probably unlikely. But the other conformation, where you just take that one edge and sort of flip it around, that leads to that twist chair, this is equally well fitting to the density. So in this case, there's probably here another solution that satisfies these constraints as well. So this is just a little bit of an illustration of how you can approach this kind of problem of figuring out what the likely conformation of a molecule is, even if it's slightly beyond the typical structures that we all know. So it's this divide and conquer method, and it really requires a tool like Conquest to ask the specific questions about how to extend the knowledge a little bit beyond the immediate substructure at hand. So this was part one of what I was going to say, and I'm going to switch to something else. So we've been working quite a bit with various groups, in particular with the CCDC, also with Matthias Rarei's group, on mining structural databases in different ways. And two of the things that came out of this work was the torsion analyzer, so essentially a library of known torsion angles that are important in drug discovery, recall for fragment replacement. And now we're onto something new, and this is a collaboration that we have with the CCDC, where Oliver Korb, who's in the audience, is the lead programmer. And now I need to explain to you why we're doing this. Why do we need yet another tool that mines databases? Well, there are questions that you cannot answer really well with current query tools. So for example, if you're interested in what other ligand motifs bind into a certain pocket, there are tools that do that, but they can be made more flexible and more powerful. Or if you have questions like which ligand motifs have similar interaction patterns in a protein or in a small molecule crystal structure. This is one of the ongoing themes for us. How do we make sure that we mine the CSD and the PDB always in parallel to draw the most of the information that we can out of both of these databases? So there's a lot more to be gained from different search tools. And the way we've approached this is by using something that we all know, namely pharmacoforce. And obviously, you all know what a pharmacophore is. There are features, they're usually spheres. They have tolerances, you can make them bigger or smaller. And we have directional features, for instance, for an acceptor here, that just roughly say where that acceptor is pointing. So it's a well-known approach, it's nothing new. Why pharmacophores? Well, it works with chemists. It's something that easily is amenable to 3D-based structuring, structure setup, so you avoid tinkering with geometric parameters. You can immediately overlay your results onto the pharmacophore and get the result back in this in the form in which you've phrased the query. And it's very flexible because you can combine it with substructures, you can adjust tolerances, you can make it work for almost any type of problem. So that's why we chose this. So the way the system now works is you define your query, that's the pharmacophore, and then you have a database of structures that are pre-annotated. Also nothing new, but effectively all these features are already pre-placed onto each structure. And then we do a search in distance space, that allows for relatively fast backtracking algorithms down here, quoted. And then later in the second step, you then take the results and overlay them onto the pharmacophore and have another filter that takes out a few solutions that still don't fit. And then, of course, you can calculate an RMSD. So it's a very simple, conceptually simple process. What's important is that the system works very quickly and fast because we can do two things essentially at the same time. So you can take the pharmacophore and look which features are you actually looking for. And in this way, you can pre-filter your database. You don't have to search the entire database. And then, of course, you can distribute the remaining actual pharmacophore search onto multiple CPUs, get your overlays, and then Oliver has, of course, a few additional tricks to make this really fast, because what you want to do is iterative searches. You really want to sit there, change the pharmacophore on the fly, see what you get, modify it again, and in this way refine your query in a very nice way. So the interactivity here is absolutely key. And this is what the system now looks like. This is a very simple query that just consists of a donor and an acceptor pair. Oops. There we go. So a little movie here that just shows you, you run this, you immediately get hits. In this case, of course, you get very many because this is such a simple query. On the side, you can see you get a 2D representation of your hits as well. Then you can browse through them. And this is real life behavior now. This is not sped up in the movie. So that's the concept. You can constantly change your query. You get a new set of hits. You can browse and so on. And just to show you how powerful that mechanism really is we've put together a query that contains different types of features that are interesting. So this is a planar ring. This is an acceptor, and this is an exit vector, which we also have as a feature. And it just denotes an element of a known kinase inhibitor scaffold. And if you take that into the system, then this is what the query looks like. You can again run it. So you can see now, click on run, you get hits. This is a CSD search. They all overlay, can do the same thing. And then, of course, look at the various different results. The CSD is very good for these kinds of queries because it contains so many different scaffolds that are partially amenable to drug design, partially not. So here you see some nice ring-opened structures where the second ring is replaced by an intramolecular hydrogen bond here as well. And so it gives you some ideas of the diversity of scaffolds that you can get with this query. So the nice thing is now you can run exactly that same query in the PDB, and this is what we're doing here. So now you see an annotated list of hits where you see what types of structures you get. It's not running anymore. There we go. Okay, now it continues. And here's also an example, if you look very quickly, how you can add an additional feature. Probably that's just me, right? Should continue now. Exactly. So now on the side you see there's a donor that's being added, and now you see protein parts coming out as part of the results. They're also overlaid. These are now truly kinase scaffolds, and it's a nice way of simply collecting all the PDB structures that contain that type of interaction motif very quickly without having to look for annotation keywords like kinase or tyrosine kinase or whatever. So it quickly gives you an overview of everything that's available in the PDB for a specific type of motif. And together then, that is really powerful information because then you can say, okay, now we compare it to existing known scaffold tops. Of course, this has been done before, in this case by Novartis. This is just a case study by Pascal Fourier and others. But it just gives you an image of how powerful and how quick you can get new results. You can do many more things, and these are a few queries now that at least I didn't know how to do before in a meaningful way. So you could be interested, for example, in these aromatic-like boxes that you have in a factor 10A S4 pocket, simply to be defined by three pharmacophore features that define phenyl rings or aryl rings, and then something in the middle that is essentially just any atom. And you can very quickly see how many different types of structures are there in the PDB of very, very different nature. Antibody complexes, as a choline binding protein that bind something aliphatic, something aromatic, or something positively charged in these kinds of boxes. So very quickly you can do these comparisons of subpockets of any size and of any shape. Another one that I really liked was this idea of comparing pockets that arise from certain folds. So for example, we all know that there are beta sheets and they have these bay areas underneath. You can in principle have a fairly lipophilic pocket. So essentially the query that's defined here just says, give me everything that has these two beta strands, the bay part of it, and something underneath, which is essentially just a placeholder for any ligand structure or element of it. And when you do that, you can quickly compare completely different proteins. For instance, HIV-RT has this feature, the rat transthyretin complex. And there's a certain preference that you see very quickly for halogen-substituted lipophilic moieties pointing into that bay area. I don't have the statistics here, but it's interesting because that kind of feature came up in earlier analysis, and also Klaus Müller did about fluorine interactions, where this is now an overlay of a number of p38 MAP kinase complexes where you have these substituted phenyl rings pointing into the back pocket, which is behind the gatekeeper residue. And we also have a bit of SAR from our own old p38 project from 15 years ago, so which all point in the same direction, namely that these fluorine interactions here are multipolar interactions that are very favorable in this particular case. So these kinds of pocket comparisons can be very powerful. You can really learn across different projects and different target classes. A word of caution. Of course, you can do these kinds of comparisons for lipophilic pockets. You can also do them for polar ones. And in that case, you really have to pay attention to detail. For instance, if you look at PDE, this is now PDE5 complexes, you get this sildenafil type interaction with a donor-acceptor pair. There's always this other amide group that hangs around with it, and you can wonder what exactly is it doing there. Sometimes there's a water, sometimes there isn't, sometimes there's something funny where you can say, well, I don't really know, is that a hydrogen bond, is it not? And then you do that query, and you find other arrangements where you have these two planar, coplanar amide groups. And for instance, these are two beta-lactamase complexes. In those cases, you always find these bifurcated hydrogen bond systems. And you could wonder, well, why don't I find them here? Well, the difference is that the two amide groups just have a slightly different distance from each other. So in the bottom case, you can see that it just rotates slightly more into the binding site. And so these two distances actually then make it possible to form these two hydrogen bonds instead of just one like up here. So here it becomes very critical to look at the details of the arrangement, also the flexibility. And there's a lot to be learned in that space, I think, going forward, because now we can really move into a phase where we don't learn about pairwise interactions only, but really interaction patterns that go far beyond just this classical concept of pairwise interactions. With this, I'm at the end, and I'd just like to thank a few people. So obviously, Oliver is the person who's programmed all this. Bernd Kuhn is the main person in Basel in the CAD group, who's been his sparring partner. Colin and Jason have made this possible, this collaboration. And of course, I know a lot more people at the CCDC who really are in the background here helping and making this possible. And I'd also like to thank, this is a great occasion, I think, Klaus Müller for being a pioneer at Roche and beyond, and we'll listen to his talk later. Thank you so much.